In the far outer darkness of the solar system, there is a planet that behaves in ways scientists did not expect. It lies nearly 4.5 billion kilometers from the Sun, in a region where sunlight is so weak that daytime would resemble a dim twilight on Earth. At that distance, temperatures plunge hundreds of degrees below freezing. Logic once suggested that such a world should be quiet and frozen, a silent planet drifting through space. But Neptune is not quiet. Instead, it hides some of the most extreme conditions ever observed on any planet. Winds that race across the atmosphere faster than a commercial jet aircraft. Storms large enough to swallow Earth itself. Pressures deep inside the planet so immense that ordinary matter may transform into something completely unfamiliar. For a long time, however, none of this was known. In the early 19th century, Neptune could not even be seen clearly through telescopes. The planet was so distant that it appeared as little more than a faint blue point of light. Yet something strange was already revealing its presence. Astronomers studying the orbit of Uranus noticed that the planet was not moving exactly where it should. According to Newton's laws of gravity, the path of Uranus around the Sun could be calculated with remarkable accuracy. But careful measurements showed small deviations in its motion, as if an invisible object were pulling on it from beyond. The discrepancy was subtle, but persistent. In 1846, French mathematician Urbain Le Verrier decided to solve the mystery using mathematics alone. Instead of searching the sky randomly, he analyzed the gravitational disturbances affecting Uranus and calculated where an unknown planet must be located. His prediction was extraordinarily precise. On September 23, 1846, German astronomer Johann Galle pointed a telescope toward the exact coordinates Le Verrier had calculated. Within minutes, he spotted a faint blue disk among the background stars. A new planet had been discovered, not because someone saw it first, but because its gravity betrayed its existence across billions of kilometers of space. That planet was Neptune. At the time, it seemed like nothing more than a distant curiosity. A cold, quiet world at the edge of the solar system. But as technology improved and scientists began to study Neptune more carefully, they realized something deeply unsettling. This distant planet was not calm at all. In fact, Neptune would turn out to be one of the most violent and mysterious environments anywhere in our planetary system, and the first real clue that something unusual was happening there would come from an object orbiting Neptune itself. A moon whose strange motion hinted that the planet's past was far more chaotic than anyone had imagined. That moon is called Triton, and its discovery would raise a new question about Neptune that scientists are still trying to answer. Long before spacecraft ever reached Neptune, one of the earliest clues that something unusual surrounded the distant planet came from a single moon. Only a few days after Neptune itself was discovered in September 1846, astronomers detected a large companion orbiting the new planet. This moon was later named Triton. At first glance, Triton appeared to be just another satellite in the solar system. But as astronomers studied its motion more carefully, they realized something deeply strange. Triton was moving in the wrong direction. Most moons orbit their planets in the same direction that the planet rotates. This is what scientists expect when moons form from the same rotating disk of material that created the planet itself. It is similar to how cars in a circular racetrack all move in the same direction because they started with the same motion. But Triton does the opposite. It travels around Neptune in a retrograde orbit, meaning it moves against the planet's rotation. To planetary scientists, this detail immediately raised a serious question. A moon moving like this almost certainly did not form alongside the planet it orbits. Instead, Triton appears to be a captured world. Modern analysis suggests Triton may once have been an independent object from the distant Kuiper Belt, a region filled with icy remnants left over from the formation of the solar system. At some point billions of years ago, Triton likely passed close enough to Neptune for the planet's gravity to trap it permanently. But capturing a large moon is not a gentle event. When Triton fell into Neptune's gravitational control, its arrival would have violently disrupted the entire system of moons that once surrounded the planet. Earlier satellites may have collided with one another, or been flung into space entirely. Some scientists believe the debris from those ancient collisions may still exist today, as the faint rings that circle Neptune. This possibility means that the peaceful blue planet we see today may have experienced a chaotic and destructive past. Triton itself remains one of the most intriguing worlds in the outer solar system. It is larger than the dwarf planet Pluto and possesses a thin atmosphere of nitrogen gas. When NASA's Voyager 2 spacecraft finally flew past Neptune in 1989, its cameras even detected faint clouds drifting across Triton's surface. But the spacecraft would soon reveal something far more surprising, because as Voyager approached Neptune itself, scientists began to notice violent motion inside the planet's atmosphere. Something powerful was happening in those distant clouds, and what Voyager discovered there would completely change our understanding of Neptune. In Part 3, the spacecraft's images reveal a planet with storms unlike anything scientists expected to find so far from the Sun. For more than a century after its discovery, Neptune remained little more than a distant blue mystery. Through even the most powerful telescopes on Earth, the planet appeared smooth and quiet. Astronomers assumed that a world so far from the Sun must be cold, slow, and relatively inactive. That assumption survived until the summer of 1989. After traveling for nearly 12 years across the outer solar system, NASA's Voyager 2 spacecraft approached Neptune. Launched in 1977 as part of an ambitious planetary exploration program, the probe had already visited Jupiter, Saturn, and Uranus. But Neptune was its final destination, the most distant planet ever explored by a spacecraft. On August 25, 1989, Voyager 2 passed just 4,950 kilometers above Neptune's cloud tops. What its cameras transmitted back to Earth stunned planetary scientists. Instead of a calm atmosphere, the spacecraft saw enormous storm systems swirling across the planet. The most striking feature appeared as a massive dark oval embedded in Neptune's blue clouds. Scientists named it the Great Dark Spot. The storm was enormous, roughly comparable in size to the entire planet Earth. But the real shock came when researchers at NASA's Jet Propulsion Laboratory began tracking the motion of the surrounding clouds. By comparing images taken minutes apart, they could measure how fast the atmosphere was moving. The results were extraordinary. Winds on Neptune were racing at speeds of nearly 2,160 kilometers per hour. That is faster than the cruising speed of a modern passenger jet, and close to the speed of sound in Earth's atmosphere. For a planet receiving less than 1,000th of Earth's sunlight, this made little sense. Normally, atmospheric winds are driven by heating from a star. Warm air rises, cool air sinks, and pressure differences create motion. But Neptune receives very little solar energy. By traditional models, its atmosphere should be relatively calm. Yet Voyager had revealed the most violent winds anywhere in the solar system. This meant the driving force behind Neptune's storms could not be coming from the Sun. Something inside the planet itself was supplying enormous amounts of energy. The question now confronting scientists was simple but unsettling. What kind of internal engine could power such extreme weather on a world so cold and distant? To answer that question, researchers would have to look far beneath Neptune's clouds, into a planetary interior where pressures reach millions of times stronger than anything found on Earth. A planet nearly 5 billion kilometers from the Sun should not be energetic. At that distance, sunlight is weak, temperatures plunge far below freezing, and most atmospheric motion should slow to a near standstill. Yet the measurements returned by Voyager 2 in 1989 told a completely different story. Neptune's atmosphere was moving with astonishing violence, producing winds faster than any ever recorded in the solar system. For planetary scientists, this created a serious problem. If sunlight was too weak to power Neptune's storms, then something else had to be supplying energy to the planet's atmosphere. The answer began to emerge in the years following the Voyager mission, as researchers analyzed infrared observations from space telescopes and planetary probes. These measurements revealed something unexpected. Neptune was not only absorbing energy from the Sun, it was also releasing its own heat. In fact, Neptune radiates more than twice the amount of energy it receives from sunlight. This discovery meant that the planet contains a powerful internal heat source hidden beneath its clouds. The phenomenon was confirmed through observations analyzed by planetary scientists, working with NASA and other international research institutions during the 1990s. But where does that energy come from? To understand the process, scientists began modelling Neptune's interior. Beneath the visible blue clouds lies a deep atmosphere of hydrogen, helium, and methane gas. Far below that atmosphere exists a massive mantle composed largely of water, ammonia, and methane ices compressed under unimaginable pressure. Inside this mantle, conditions become extreme. Pressures can reach millions of times greater than the atmospheric pressure at Earth's surface. Temperatures climb high enough to transform ordinary materials into exotic states of matter. Under these conditions, heat trapped since the planet formed billions of years ago may still be escaping slowly outward. As this internal energy rises, it stirs Neptune's atmosphere from below, driving powerful convection currents that accelerate winds across the planet. A simple comparison helps explain the effect. Imagine heating water in a pot. Even before the water begins to boil, warmer fluid at the bottom starts to rise while cooler fluid sinks. The constant circulation creates motion throughout the liquid. Something similar appears to be happening inside Neptune, but on a planetary scale. The internal heat rising from deep within the planet acts like a hidden engine, feeding the massive storms and extreme winds observed in its atmosphere. Yet the deeper scientists studied Neptune's interior, the stranger the planet seemed to become, because inside that crushing mantle, researchers began to suspect that something extraordinary might be forming, materials that do not exist naturally anywhere on Earth. In the next stage of the investigation, scientists would explore the possibility that deep inside Neptune, the immense pressure may trigger a process unlike anything found on our planet, a process that could cause an alien form of precipitation, a phenomenon sometimes described as diamond rain, and the physics behind it would reveal just how extreme Neptune truly is. Deep inside Neptune, far below the clouds visible to telescopes and spacecraft, pressure becomes so intense that ordinary chemistry begins to behave in extraordinary ways. Scientists believe that thousands of kilometers beneath the planet's atmosphere, the pressure reaches levels close to 7 million times stronger than the air pressure at Earth's surface. At the same time, temperatures climb to thousands of degrees. In such an environment, familiar molecules cannot remain stable for long. Among the gases present in Neptune's atmosphere is methane, a simple molecule made of carbon and hydrogen. On Earth, methane exists as a gas in swamps, lakes, and even in our own atmosphere. But inside Neptune, methane may undergo a dramatic transformation. According to theoretical models developed by planetary physicists during the 1990s and later tested in laboratory experiments in the early 21st century, extreme pressure can break methane molecules apart. When this happens, the hydrogen atoms separate, leaving behind pure carbon. Carbon under enormous pressure does something remarkable. It crystallizes. In other words, the carbon atoms may reorganize into diamond. This idea moved from theory toward experimental support in 2017, when researchers at the SLAC National Accelerator Laboratory in California recreated similar pressure conditions using powerful lasers. The experiment showed that hydrocarbons exposed to intense pressure could indeed produce tiny diamond structures. If similar processes occur naturally inside Neptune, the implications are extraordinary. Within the planet's deep mantle, microscopic diamonds could begin forming in vast quantities. These crystals would be far denser than the surrounding material, causing them to sink slowly downward through the superheated interior. Over time, Neptune could experience a strange form of precipitation. Instead of water droplets falling through clouds, solid carbon crystals might descend through the mantle like glittering hailstones. The phenomenon is sometimes described as diamond rain. Of course, these diamonds would not resemble polished gemstones. They would likely melt or transform as they fall deeper toward the planet's core. But the physics behind the process reveals just how alien Neptune's interior truly is. Yet diamonds are only one part of the story hidden beneath the planet's clouds. As scientists continued studying Neptune's structure, another mystery began to emerge, one involving invisible forces surrounding the entire planet. For reasons that remain only partially understood, Neptune's magnetic field behaves in ways unlike almost any other planet in the solar system, and understanding that strange magnetic environment would reveal another layer of Neptune's unsettling nature. Space around a planet is rarely empty. Invisible forces extend far beyond the clouds, shaping how charged particles move and how energy flows through space. Around Earth, this protective bubble is known as the magnetosphere, generated by motion deep within the planet's molten iron core. For most planets, magnetic fields behave in predictable ways. They are roughly aligned with the planet's rotation, forming symmetrical structures stretching into space. Scientists expected Neptune to follow the same rule. But when NASA's Voyager 2 spacecraft flew past Neptune on August 25, 1989, its onboard magnetometer detected something deeply unusual. Neptune's magnetic field was dramatically tilted. Instead of lining up with the planet's rotation, the magnetic axis was found to be tilted by nearly 47 degrees. Even stranger, the magnetic field was not centered inside the planet at all. It appeared offset, displaced thousands of kilometers from Neptune's geometric center. To understand why this matters, imagine a spinning top with a flashlight inside it. If the beam points straight through the center, the light sweeps the same path every rotation. But if the flashlight is crooked and shifted to one side, the beam traces a distorted and constantly changing pattern. That is essentially what happens around Neptune. As the planet rotates, its uneven magnetic field twists and shifts through space, producing a magnetosphere unlike any other known planetary environment. Charged particles from the Sun interact with this tilted field in complex ways, creating faint auroras that appear not only near the poles, but also across mid-latitudes. Planetary scientists analyzing Voyager 2 data in the early 1990s concluded that Neptune's magnetic field likely forms in an unexpected place. Instead of originating in a metallic core like Earth's, it may be generated in a vast layer of electrically conducting fluid within the planet's mantle. This theory suggests that Neptune's interior is far more complex than scientists once imagined. Beneath the clouds and beneath the diamond-forming mantle may lie enormous layers of exotic fluid, capable of generating powerful magnetic currents. But Neptune's magnetosphere is not the only structure surrounding the planet that behaves in unexpected ways. Beyond the clouds, beyond the magnetic field, something else circles Neptune in near darkness, a set of rings so faint and strangely shaped that their existence once puzzled astronomers. And the way those rings behave may reveal that Neptune's past was far more violent than it appears today. At first glance, Neptune appears smooth and featureless from a distance. Its deep blue color hides details that are extremely difficult to detect from Earth. For decades after the planet's discovery, astronomers believed Neptune might not possess rings at all. That assumption began to change in the late 20th century. During the early 1980s, astronomers observing distant stars noticed something strange when Neptune passed in front of them. The starlight briefly dimmed before and after the planet crossed the star. These short flickers suggested that something thin and dusty was orbiting Neptune. In 1984 and 1985, teams studying these stellar occultations proposed that Neptune must have rings, but the pattern of the dimming was inconsistent. Sometimes the light faded, and sometimes it did not. The data seemed contradictory. When Voyager 2 finally arrived at Neptune in 1989, its cameras provided the first clear images of the planet's ring system. What scientists saw confirmed that the earlier observations had been pointing toward something truly unusual. Neptune does indeed have rings. But unlike the bright, continuous rings of Saturn, Neptune's rings are extremely faint and incomplete. Instead of forming perfect circles of evenly distributed particles, parts of Neptune's outer ring appear clumped together into bright segments known as arcs. These arcs were not supposed to exist. According to classical orbital physics, particles in a ring should spread evenly around the planet over time. Gravity and motion naturally distribute the material into a uniform band. Any clumps should disperse quickly. Yet Neptune's ring arcs have remained stable for decades. Scientists believe the answer may lie in subtle gravitational interactions with nearby moons. Small shepherd moons could be acting like invisible barriers, preventing ring particles from spreading out and instead trapping them in narrow regions. Even so, the precise mechanism remains uncertain. The arcs within Neptune's outer Adam's ring continue to challenge planetary models. Their persistence suggests that Neptune's gravitational environment is far more complex than it first appears. But the rings themselves may also be evidence of something even more dramatic. Some researchers believe the debris forming these rings could be the remnants of ancient moons destroyed long ago. If that idea is correct, Neptune's calm appearance today may hide the aftermath of catastrophic collisions in the distant past. And one moon in particular may hold the key to understanding how violent that history might have been. That moon is Triton, a world whose strange orbit suggests it may not belong to Neptune at all. Among all the objects orbiting Neptune, one stands apart from the rest. Its orbit is wrong. Most moons in the solar system travel around their planets in the same direction the planet spins. This happens because planets and their moons usually form together from the same rotating cloud of gas and dust. Everything begins with the same motion, so everything moves in the same direction. But Neptune's largest moon, Triton, breaks that rule. Triton orbits Neptune in the opposite direction of the planet's rotation. Astronomers call this a retrograde orbit. For planetary scientists, that single detail reveals something extraordinary. Triton almost certainly did not form with Neptune. The moon was first discovered in October 1846 by British astronomer William Lassell, only weeks after Neptune itself had been identified. For many decades, it appeared to be simply a large and distant satellite. But as telescopes improved during the 20th century, its unusual orbit became clear. Modern planetary models now suggest that Triton likely originated far beyond Neptune in a region known as the Kuiper Belt. This distant zone is filled with icy remnants left over from the formation of the solar system more than 4 billion years ago. At some point in the ancient past, Triton may have passed close to Neptune. The planet's gravity captured the object and forced it into orbit. But capturing a large moon is not a quiet event. When Triton was pulled into Neptune's gravitational influence, the sudden disturbance would have reshaped the entire system of moons surrounding the planet. Earlier satellites may have collided with one another or been thrown out of orbit entirely. Some scientists believe the debris from those ancient collisions could still exist today, as the faint rings circling Neptune. The arrival of Triton may therefore have triggered one of the most violent transformations in the history of the outer solar system, and Triton itself remains a deeply unusual world. When NASA's Voyager 2 spacecraft flew past Neptune in August 1989, its cameras revealed something unexpected on the moon's frozen surface. Instead of a dead and inactive landscape, Triton showed signs of geological activity. Voyager detected dark plumes rising above the surface, geysers erupting nitrogen gas high into the thin atmosphere. Even in the frozen darkness of the outer solar system, Triton appeared to be alive with motion. But Triton's strange orbit raises another long-term consequence, because over immense stretches of time, gravitational interactions between Neptune and Triton are slowly changing the moon's path. And those changes suggest that Triton's future, and Neptune's, may eventually lead to a dramatic outcome. Far beyond Neptune's clouds, a slow and invisible process is unfolding. It is not dramatic on human timescales, no explosions, no sudden storms. Yet according to planetary physics, this quiet process may eventually transform the entire Neptune system. The key to this future lies with Triton. When NASA's Voyager 2 spacecraft flew past Neptune in August 1989, scientists obtained the most precise measurements ever made of Triton's orbit. Analysis by planetary researchers at NASA's Jet Propulsion Laboratory revealed an important detail. Triton is gradually spiraling closer to Neptune. This movement is caused by tidal forces. Whenever two massive bodies orbit each other, gravity stretches them slightly. On Earth, the moon pulls on our oceans and produces tides. But tides do not only move water, they also slowly exchange energy between orbiting objects. In Triton's case, the tidal interaction with Neptune is draining orbital energy. Over extremely long periods of time, this causes the moon's orbit to shrink. The change is incredibly slow. It unfolds across tens or even hundreds of millions of years. but the mathematics describing this process is well understood, and the long-term outcome is difficult to avoid. Eventually, Triton may cross a critical boundary known as the Roche limit. The Roche limit marks the distance where a planet's gravity becomes stronger than the internal gravity holding a moon together. When an object passes inside this boundary, tidal forces begin to tear it apart. If Triton ever reaches this region, Neptune's gravity could slowly pull the moon to pieces. Instead of a single large satellite, the fragments would spread into orbit around the planet, forming an enormous ring system made from the debris of an entire moon. Planetary scientists believe this process may have already happened elsewhere in the solar system. Some researchers suggest that Saturn's rings could be the remains of a destroyed icy moon. If the same fate awaits Triton, Neptune could one day possess rings far brighter and more massive than the faint arcs we observe today. In that distant future, the calm blue planet would be surrounded by a brilliant disk of shattered ice and rock. But this possibility raises a deeper question. Neptune already challenges many of our expectations about distant worlds, from supersonic winds to diamond-forming pressures deep inside its mantle. What does a planet like Neptune tell us about the kinds of worlds that may exist beyond our solar system? To answer that question, scientists must step back and look beyond Neptune itself, toward the growing catalogue of planets orbiting other stars. At the edge of our solar system, Neptune once seemed like a quiet and distant world. For much of human history, it appeared as nothing more than a faint blue dot, barely visible even through powerful telescopes. But every major investigation of this planet has revealed something unexpected. Supersonic winds racing across a frozen atmosphere, hidden internal heat powering violent storms, pressures deep inside the planet capable of transforming ordinary carbon into diamonds, a magnetic field twisted far away from the planet's center, and a captured moon whose orbit suggests that Neptune's past was shaped by powerful gravitational chaos. Taken together, these discoveries change the way scientists think about planets. When NASA's Voyager 2 spacecraft passed Neptune in August 1989, it provided humanity's first close look at this distant giant. The mission revealed that the outer solar system is not a quiet frontier, but a place where powerful forces are still shaping planetary worlds. In the decades that followed, astronomers began discovering planets around other stars. By the early 2000s, surveys using large observatories and space telescopes had detected hundreds of these distant worlds. As the number grew into the thousands, a pattern began to appear. Many of the most common planets in the galaxy appear similar in size to Neptune. They are not massive gas giants like Jupiter, and they are not small rocky worlds like Earth. Instead, they belong to a category astronomers often call ice giants, or mini-Neptunes, planets with thick atmospheres, deep interiors, and complex weather systems. This realization transformed Neptune from a distant curiosity into something far more important. It became a laboratory. By studying Neptune, scientists gain clues about how these common planetary worlds behave, how their atmospheres circulate, how their interiors generate heat, and how gravity shapes their moons and rings. Yet despite everything we have learned, humanity has only visited Neptune once. One spacecraft, one brief encounter lasting only hours. Beyond the clouds, the storms continue to move. The rings remain faint and mysterious. Triton still circles the planet in its strange reversed orbit. And deep beneath the atmosphere, the immense pressures of Neptune's interior continue their silent work. The planet that once seemed distant and quiet has become one of the most revealing worlds in our solar system. And somewhere within that deep blue darkness, Neptune may still be hiding discoveries that future explorers have yet to uncover.